The outline of our presentation, I'll start first with the introduction, about the log transformation, problems, use, and problems. This is a prevalent transformation used in astronomy and physics. It's also commonly used in biology, ecology, and medicine. It's prevalent in economics and business, and nearly absent from use in biochemistry and biophysics. There are several general pitfalls that we will examine. Skewed data and data variability, parameter problems from log transformed data including information loss, incorrect statistical indicators. And we will use an example from astrophysics. The number one problem in astrophysics now is analyzing supernova data. We will present examples of poor modeling and of better modeling of astrophysical data. And note that improper analyses leads to incredible claims. And then that will be followed by a quick summary, suggestions, and outlook. And then please stick around for the credits and the references at the very end. Now, the log transformation problem is widely used to improperly deal with skewed or noisy data. Some believe that the log transformation decreases data variability, which is usually not true. Analysis performed with log transformed data often present irrelevant results when compared with results using non-transformed data and proper modeling. Researchers should not use this flawed method when dealing with data, but rather use modern computerized curve fitting techniques with untransformed data. And it may be better in many studies to collect better data. Skewed data with the log transformation. The following several arguments are a sketch from a publication by Feng et al. In 2014. Data from many studies do not approximate normal distribution. Applying this log transformation does not reduce the distribution skewness, but often makes this problem worse. We present simulated data which are uniformly distributed between 0 and 1 with two variables as presented in equation 1 below. Histograms for x sub I and y sub I are presented on the next frame. You notice that the original data, x sub I, is presented in the left graph, and the log transformed data is presented in the right graph. Note that the log transformed data is actually more skewed than the original data. Log transformation doesn't help a bit. The skewed problems with log transformation. The log transformed data, y sub I equals log the Napierian log of x, is more skewed than the original data. The skewness coefficient for the log transformed data is 1.16, but originally it was only 0.34. This skewness is an example that has been exacerbated using the log transformation. If your data is seriously skewed, you need to solve your problem with better data, not using log transformation. Your data may suffer significant systematic error or simply be noisy. Use better science to solve these problems rather than use log transformation. Data variability. Log transformation may often increase, not reduce, data variability. Consider the following simple linear regression with only an intercept term as equation 2 below. With the error term uniformly distributed between minus 0.5 and plus 0.5. Thus, y sub I in this model does not follow a log normal distribution, and the log transformed y sub I does not have a normal distribution. Data variability with log transformation. Simulating the data of Y sub I for this model with a sample size, n of 100, values for beta sub naught parameter of 1 and 5.5. Table 1 presents original and the log transform estimates of beta sub naught and the errors averaged using Monte Carlo simulations from fitting a linear model. Table 2 presents the same data with the addition of 4 outliers. So n here, the number of samples is 104. We see in Table 1 that the simulation results for the simple linear regression using log transformation and of the linear regression using the simple data itself is the linear regression returns values of beta sub naught that are very reasonable, but the log transformation of this data returns values of beta sub naught that are very unreasonable and not anywhere near the original beta sub naught. Notice that the errors associated with the log transform seem rather reasonable, so the error from this transformation really is very misleading. Table 2 presents simulation results for the simple linear regression with 4 additional outliers, 104 points, 100,000 simulations. Note once again that the original data, a linear assay, returns beta sub naught pretty close to the original estimates. But note that the log transformation returns beta sub naughts that are really very unreasonable and do not align very well with the original beta sub naught. Problem of parameters that are assayed using log transformation. The mean of the log transformation observations, the log of Y sub I, presented in equation 3, is often used to estimate the mean of the original data by applying the anti-log function as the exponential of the log transformed mean. The inversion of the mean log does not usually result in an appropriate estimate of the mean of the original data. This value is more correctly exponent of mu, the average, plus the standard deviation squared divided by 2, not the simple exponential of mu, where sigma is a standard deviation. The log transformation of correlation data also results in information loss. There is no real number, the y-axis intercept. That parameter is lost and cannot be retrieved. Using the log transformation, you lose valuable information. Here we will use an example from Astrophysics. No long introduction of astrophysics. You could check out many textbooks on cosmology. We will skip the typically long introduction and refer the viewer to several books covering the subjects of universe origin and the current state of the universe. These are references 1 through 5. They're available at the end of this video. There are many other introductions to cosmology, and many audio-visual presentations are available on YouTube. References 6, 7, and 8. We are interested in calculations of the Hubble constant, h sub naught, the normalized matter density, omega sub m, of the universe, and the chi-squared test result for the chosen models. The better fit is considered that with the smaller chi-squared. Many people are also interested in calculating values of lambda, that is, omega sub lambda, which has been related to dark energy. Some people are also interested in the value for omega sub k, that is, the influence of space-time. For determination of these parameters, we need as much data as possible of the distances, d sub l, and the recession velocities of far-flung galaxies. That is, the distances here will be the luminosity distances. Example from astrophysics, the problem with the distance data. Light emitted from supernova type 1a are thought to mimic standard candles. They are used as distance indicators. This light is from billions of years ago and estimates d sub l. Data from supernova type 1a thermonuclear explosions are called SNe Ia are collected by several large telescopes during the last decade of the 20th century. The Riess group used data from 27 supernova previously collected by Hamui, that's reference 10, In addition to their data from 10 new supernova independently collected by them, for a total of 37 supernova, we use that collection to demonstrate some pitfalls of using log transformation with noisy data. Oh, here's a nice example of the remnants of a supernova. This is a supernova remnant Cassiopeia. This is a photograph from the NASA public files, a beautiful, beautiful remnant of a supernova. The supernova problems, choosing variables. The observations are supernova type 1a, luminosity magnitudes m, the magnitude error, and the paired redshift zeta or z, which is determined from the associated galaxy wavelength shift, that is delta sub lambda. And that is presented as equation 4 here. For distant supernova, the redshift is always positive, which means and indicates the supernova is moving away from us. The larger redshift means greater velocity. Luckily for astrophysics, we can use spherical geometry with polar coordinates to greatly simplify our data and analyses. The magnitude m is often used by astronomers as values for the distance. Note that the magnitude m is not the supernova luminosity distance, d sub L, but is related to the luminosity distance by equation 5. Equation 5 is in fact a log transformation of the luminosity distance. The magnitude m does not have any units and is not a metric. Values for m and redshift are often used for parameter determinations, such as the Hubble constant, omega sub m, omega sub k, omega sub lambda. To estimate m, the magnitude, astronomers track a supernova emission decay for several days and correlate this decay to the intrinsic luminosity of the supernova. Many problems for m, precision, and accuracy exist. Intervening dust scatters the emission light. The nature of the associated galaxy affects the light, the emission light. That's reference 11. The mechanism of the explosion. It's either slow matter accretion or a star-star collision. Wavelength dependence of the emission. Note that in reference 12. Asymmetric, that is a non-spherical explosion. Values of m are suspect, so m becomes the dependent variable. Here m sub b means the values from blue visible light. And we should summarize all these problems is that there is a lot of problems in determining the distance of these explosions from the observation. And here, just to highlight such problems we have, is a nearby type 1 event with several problems, and this was observed originally by people in London University. And the supernova 2014J from the neighboring galaxy M82 presents a lot of the problems we just presented. Dust seems to be an incredible problem. Here we have a supernova emission from an extremely dusty galaxy. And how is one best to judge light extinction from a dusty galaxy? In figure 4. Example astrophysics. The Friedmann-Robertson-Walker cosmology, the FRW cosmology, a variation of this model of the universe expansion for a presumed flat universe is used to estimate the parameters, the Hubble constant, omega sub m, and omega sub lambda. Omega sub m is the normalized matter density, and omega sub lambda is the normalized cosmological constant, lambda, which is considered to be dark energy. And the normalization is presented in equation 6. The Friedmann-Robertson-Walker relationship is most often cast using spherical coordinates, with the luminosity distance, d sub L, being the radial distance. This model is consciously cast in terms of radial distance and radial velocity, coordinates and motion used for the last 100 years to solve a multitude of problems in physics. The FRW relationship in terms of d sub L and redshift is used by the groups Riess and Perlmutter, was supposedly that presented in equation 7 below. Here the redshift is often used in the transformed version of the recession velocity. What was really used to analyze the data of Riess is a relationship equation 8, and we can see that that is a log transformed relationship. This relationship is for using log transformed data, that is the magnitude m. Note that m sub e has no units, being log transformed, no metric on the next figure, and m sub e is not the dependent variable in the Friedmann-Robertson-Walker model. Also note the errors assigned to distant supernova on the next graph are only slightly larger than to more nearby supernova. And note that a redshift of about 1 is about halfway back to the Big Bang. Here in Figure 5, we had an example taken from the Riess publication in 1998. That's reference 13. This is fit to equation 8, not to equation 7. Nearby supernova are on the left. Very distant supernova are on the right. Note that the errors associated with these magnitudes are really not increasing very much as one looks back halfway to the Big Bang. Something a little bit suspicious here. The relative errors can be easily seen in Figure 6, the next frame, where the redshift is transformed into log zeta for this log-log plot. The relative errors are quite similar for all the data, irrespective of the log of z, that is, independent of being near or far from the observatory. Another publication presents a log-log plot with more supernova data, here in Figure 7, that's referenced in 14. Where is the solar system located in these figures, Figures 5, 6, and 7? This evidence for ignorance results from the loss of a variable with log transformation of the data. Here we have the magnitude, the blue filter, versus the log of the redshift on the x-axis for the 37 supernova as reported by Riess. Note again the errors for distant supernova are not that much larger for more recent supernova. Here is another plot from a publication in the National Academy of Science, 2004, by Kirshner, reference 14. The more distant supernova toward the top right, the more recent supernova toward the bottom left. Again, the errors do not increase dramatically as one would expect as one gets halfway back toward the Big Bang. And there is no position for the Earth either. The position of the Earth is lost because we have lost that information by running a log transformation. A similar analysis using log transformation of another collection of 42 supernova was presented by Perlmutter in 1999. That's reference 15. Figures from that paper are reproduced here as Figures 8 and 9. One should notice the errors for distant supernova are not much larger than those of nearby supernova, which are best seen in Figure 9. Error estimation is of paramount importance since proper modeling is heavily dependent on error assignment. So the parameters, the Hubble constant, omega sub m and omega sub lambda, calculated using this analytical technique, and these data are very suspect. And here we present in our Figure 8, once again you see magnitude sub b, that is the blue light of the observations, are plotted versus the redshift zeta on the x-axis. And once again you see the errors associated with very distant supernova are not much larger than that associated with nearby supernova. And there was no place for the Earth on this graph either. And this is a little bit better presentation in our Figure 9 of the errors associated with the Perlmutter data and also the residuals. And you could see that the standard deviation of the fit does not lead one to suspect that the errors associated with distant supernova are that much different than errors associated with more recent supernova. Using the luminosity distance, that is the actual luminosity distance rather than the magnitude, and the expansion factor from the Friedmann-Robertson-Walker model rather than the redshift, where The expansion factor is related to the redshift in this small equation here. We present that in the next plot. And we use the real Friedmann-Robertson-Walker model for a flat universe in terms of the luminosity distance versus expansion factor, as presented in equation 9. The independent variable is the expansion factor, which currently is 1. We know where we are, and is always less than 1 in the past. And here we can solve directly for the Hubble constant and the omega parameters. This model is used with the luminosity distance and the expansion factor and presented in figure 10. Here is figure 10. This is an example of better modeling. Now our Earth is the point 1 naught at the bottom right, and the distant supernova are all the way toward the left. These are the data from Riess that he used in 1998. And you could see the distant supernova present very much larger errors than the more recent supernova toward the bottom right. This is one expects. It's very difficult to estimate distances, and one really expects the errors associated with distant observations to be much, much larger than those associated with closer observations. The next example, figure 11, presents a distribution of residuals from that fit of equation 8 to the 37 supernova from Riess. Note the residuals are no larger for distant supernova than for nearby emissions. This is not true when equation 9 is fit to these data, as displayed in figure 12, where the residuals for more distant supernova display much larger values than nearby supernova. And here are the residuals versus the redshift from the 37 supernova data from Riess. And you notice the residuals for nearby supernova are very similar for the residuals from very distant supernova. And here are the residuals when one uses the data from Riess but fits the direct model for the Friedmann-Robertson-Walker. And here you notice that the distant supernova, which are on the left half of this graph, are much, much larger than residuals from nearby supernova, which are on the right part of the graph. And we found our Earth again. That's a 0.0. We know where we are. The next example presents 4 decades of magnitude, m. Here is mu, and the distribution of residuals from the log transformation of hundreds of supernova data from a recent collection published in 2016. Again, the values of the residuals are no larger for distant supernova than nearby emissions in figure 13. An important parameter calculated from the data is the Hubble constant. But should we really trust this value knowing that the log transformation does not represent reality? Again, where is our Earth on this plot? This is a recent example from Astrophysics publication. This is more log distance data. And here you can see the residuals at the bottom half of the graph. They're not much different from recent supernova than for very distant supernova. This is hundreds of supernova. Questionable results from astrophysics. Differences for the results between the log transformation and untransformed data are significant. For figures 10 and 12, plots using untransformed data, the errors and residuals of the luminosity distance reflect the range of the supernova emissions. Residuals and the standard deviations of distant emissions are significantly larger than for more recent supernova emissions. We found our own solar system in figure 10. This is the point 1, 0, which is assigned with 0 error. We know where we are. The parameters derived from the best fit of equation 9 are also significantly different from those derived from the log transform data, as presented in Table 3. Table 3 comparisons. We have performed tests with equations 8 and 9 as models using either the magnitude redshift or the luminosity distance and expansion factor as the data sets. A least squared robust fitting routine which discriminates against outliers, was used here. Here, robust means the Pearson least squared minimization routine. And this is supposedly what is used by Riess and Perlmutter groups. We have also tested a reasonable version of the FRW model for the universe without dark energy in terms of the luminosity distance and expansion factor as equation 10. Here we use omega sub k rather than omega sub lambda. Omega sub k represents the normalized value for the influence of space-time. The terms omega sub m and omega sub k are normalized as usual as presented in the equation. This model, reference 17, is fit to values of the luminosity difference versus expansion factor, and the parameters are presented in Table 3, with the residuals presented in Figure 14. And here in Table 3, we see in the first two rows the parameters that we fit here versus the parameters that Riess found that were published in 1998. And we see that the parameters omega sub m is very similar to the Riess parameter, and we see that the value that we found for the Hubble constant is very, very similar to that found by Riess in 1998. So our fitting routine is very similar to that used by Riess. Now, when we plotted the data as presented in rows 3 and 4, when we ran the fits using the luminosity distance rather than the transform data, we got the parameters of omega sub m and the Hubble constant presented in rows 3 and 4, significantly different from that found by Riess. When we fit the data using the FRW model and using the luminosity distance and the expansion factor, but fitting using omega sub k rather than omega sub lambda, we found the value for omega sub n to be very, very small, and we found a Hubble constant very significantly smaller than that proposed by Riess. But over on the right-hand column, we found that using the omega sub k rather than omega sub lambda, we found our fit was significantly better when we fit using the parameter omega sub k rather than omega sub lambda. In other words, one can really not justify the proclamation that our universe is driven by dark energy. Now we discuss our results. The goodness of fits, as judged by the reduced chi-squared, is the same, we found here is the same 1.19 for both Riess and us. That is, when we fit using equation 8, the log transform data, our results are very similar to those published by Riess. The residuals from the fit using the luminosity distance to the expansion factor are shown in the next frame, Figure 14. Note the residuals for distance data are significantly larger than for the more nearby supernova, as would be expected in reality. The notion of dark energy receives support from observations of the cosmic microwave background, reference 18. This is a preferred model and requires 6 to 9 parameters, which means that many other models will also fit the CMB data very well. The data from the Planck observation must be extraordinarily good to allow model discrimination between all the different models which will fit the CMB data very well. Also, I might personally note that I can take a equation with 6 to 9 parameters. I can drive a truck through that and get it a good fit. We have provided data from Riess, his publication in 1998, in the appendix for students to practice and reproduce our results. And here is Figure 14, the residuals versus expansion factor, considering space-time, omega sub k, not dark energy. This is using the 37 supernova from Riess in 1998 and our earthly location. And once again, we note that the residuals are much larger for distant supernova than for more recent supernova. Sounds like reality. Here's our conclusions. The standard deviations and fitting residuals from several astrophysical publications do not reflect the reality of increasing error with increasing distance. The measure of the goodness of fits, the reduced chi-squared, to the log-transformed data appear abnormally depressed. The resulting parameters from fits using log-transformed data should be similar to parameters from fits of distance and expansion factor, but these are not similar. The use of log-transformed data forces a loss of the intercept, which should be used to check the results. To summarize, using log-transformed data often recasts the data as more skewed and with more variance. Using log-transformed data can present parameters, residuals, and statistics too good to be true. Incorrect fit statistics may point toward the wrong model. Our example problem of astrophysics. Analysis of the supernova data were and still are the main support for the notion of dark energy. Astronomers use only log-transformed supernova data to fit models supporting the notion of dark energy. This flawed method is shown here to present unrealistic results. Astronomers did not properly analyze the supernova data before proclaiming dark energy in 1998.
You failed.
To summarize, too, if astronomers had properly analyzed these data, should an accelerating universe expansion been proposed in 1998? Don't be too embarrassed if you were taken in by these claims for dark energy. Many who should not have are. That's references 19 to 24. Many famous astrophysics. It's pretty obvious that famous theoretical physics obviously do not bother to do homework any longer. The student may wish to practice curve fitting using the supernova data and transform values provided in our appendix. Suggestions and outlook. We have shown that dark energy is suspect and probably not real. This is a reason why there has been no progress toward understanding dark energy the past 2 decades, and no real progress will be made in the future. Astronomers should reanalyze their supernova data without using log transformation and reevaluate their support for dark energy. I really doubt that famous astronomers are capable of self-reflection and correction, so the above suggestion is realistic and stupid. Unfortunately, politicians will eventually also realize the nature of this perpetuated mistake and will use this for their own ignorant and self-serving devices. Why do famous astronomers continue to analyze supernova data in a manner which was abandoned by biophysicists several decades ago? Because the results are usually wrong? There is no reason for a student to transform data. Choose a better model, collect better data, analyze the data using a modern curve-fitting program. There are tons of good curve-fitting programs available, and many of them are much better than log transformation. What's next? Our optical horizon, R sub h, and curved space-time, derivation of the optical horizon for expanding universe, estimating distances using some similar formulas, and observational evidence for curved space-time. We have previously presented the video, Einstein field equations to microscopic gravity. And here's our credits, which we proudly present on our last slide. And stick around for our references, and for the student, stick around for the data in the appendix and do your homework.